Imagine you're sitting in the middle of this high-stakes meeting, or maybe you're staring at a monitoring dashboard, and suddenly the whole system just goes down.
Oh, yeah, the worst nightmare.
Right. A critical project is unraveling in real time. Your deadlines are instantly vaporized. The client is livid, and every single person in the room slowly turns their head to look directly at you.
Yep, all eyes on you.
In that exact fraction of a second, as the adrenaline spikes and your vision narrows, how do you keep from freezing? Or, I mean, even more dangerously, how do you keep from opening your mouth and plunging the entire situation into total chaos?
Well, that moment of paralysis is something, every professional faces eventually. And the instinct we have in that split second is almost universally counterproductive.
Because we want to fix it immediately.
Exactly. The human brain craves resolution, so we feel this overwhelming urge to instantly have the answer, or to reassure the room, or to just aggressively take charge by throwing out a theory.
It feels like leadership.
It does. It feels like leadership, but that impulse is actually a massive trap.
So today's deep dive is going to explore exactly how to rewire that instinct. We're looking at a really fascinating stack of historical analysis, operational notes, and system engineering debriefs that basically break down the hidden disciplines of the Apollo space program.
And to be clear, our mission today isn't just to recount space history for the sake of nostalgia.
Right. No, we are extracting highly practical, battle-tested strategies. We're talking about bounding uncertainty, managing risks, and using a very specific communication sequence to navigate those high-stress scenarios in your own daily life.
Because the defining characteristic of the Apollo program wasn't just, the engineering feat of reaching the moon. It was the fact that these teams encountered terrifying, literal life or death anomalies on a regular basis.
Constantly.
Right, and they built this unbreakable psychological machinery to handle them. When you listen to the original audio transcripts, the composure you hear from the astronauts and the controllers, it wasn't some innate superhuman bravery.
So it's trained.
It was manufactured. It was a strict operational system. And because it's a system, you can learn it and apply it to whatever you do at work.
Okay, let's unpack this. Before you can successfully solve a crisis, you have to understand the psychological trap that immediately makes it worse. The sources refer to this as the human instinct to narrate a catastrophe.
Yeah, narrating a catastrophe. When we're frightened or when we're operating under extreme ambiguity, there's a powerful pull to just panic out loud.
Like saying the whole network is crashing.
Exactly, or everything is falling apart. We instantly start guessing at the root cause. And the insidious part of this behavior is that guessing often feels like competence when you're under pressure.
Well, it feels like you're doing something, right? Standing there silently while a server burns or a deal collapses, that feels like failure. So you just start throwing out theories to prove you're engaged.
But the problem is, by throwing out those theories, you are resolving ambiguity way faster than the actual data allows. You're constructing a fictional narrative before you even have the facts. And the sources point out that this generates what they call unbounded fear. Unbounded fear is paralyzing. It completely overwhelms a team.
So what was the Apollo habit for that?
The Apollo habit designed to counter this was a strict rule. Describe reality more precisely instead of more dramatically. You have to substitute emotional storytelling with specific, raw facts and numbers.
Because doing that converts an overwhelming, unbounded fear into a bounded, solvable question.
Precisely.
Let's ground this in a familiar setting. Think about an emergency room. If a bystander rushes through the double doors screaming, "They're dying, there's blood everywhere, their heart is stopping," I mean, it just causes a ripple of chaos.
It spreads panic.
Yeah, the fear spreads because it's unbounded. But if a paramedic rolls that same patient through the doors and calmly states, blood pressure is 80/50, heart rate is 130, the dynamic changes completely.
The medical team doesn't need the dramatic narrative. They need the raw measurements.
Exactly. The paramedic took an unbounded terror and bounded it into a specific physiological puzzle. So how did this precise measurement discipline actually play out in a spacecraft?
A perfect illustration of this is Apollo 12. Just 43 seconds after the rocket lifted off the pad, it was struck by lightning.
43 seconds.
Yeah. Warning lights illuminated across the entire command module panel. They were accelerating toward orbit, shaking violently, and essentially the spacecraft's electrical systems were dying around them.
So the commander, Pete Conrad, had every reason to narrate a catastrophe.
He absolutely could have said we were hit by lightning, the ship is dead, we're going to crash. Instead, he substituted narration for precise measurements.
He just read the raw symptoms of the machine.
Yep. He got on the radio and simply said, "Bus has dropped out, where are we going?" And I just lost the platform.
Okay, let's clarify those terms for a second, because that jargon is important. When he says buses, he's talking about the main electrical power distribution lines in the spacecraft, right?
Yeah.
Correct. The buses are the primary circuit's routing power. And when he says he lost the platform, he's referring to the inertial measurement unit.
The gyroscopes.
Right, the intricate system of gyroscopes that tells the spacecraft its attitude or, which way is up. So Conrad is reporting 3 raw observations. Main power is failing, guidance is acting erratically, and the gyroscopes are offline.
No theory, no diagnosis.
And no panic. Because of that discipline, a flight controller down in Houston named John Aaron was able to look at the scrambled data coming across his screen and recognize a very specific telemetry pattern.
He'd seen it before.
He had seen that exact scrambled pattern once before during a ground test months earlier. Within seconds, Aaron provided a fix. He told the crew to reset the signal conditioning equipment and save the mission.
Which is wild. If Conrad had tried to sound smart, like if he had offered his own premature theory about what the lightning did to the hull, John Aaron would have been stuck debugging Conrad's psychological interpretation.
Exactly, instead of debugging the spacecraft's actual electrical system.
Which actually brings up a huge point, and I'm going to push back on this a little, because if you're listening to this, you might be thinking, wait, if I am the senior developer looking at the broken code, or the account manager talking to the angry client, aren't I naturally the best person to diagnose the problem?
You'd think so.
Right. Like, I have the most context. Shouldn't I offer my theory to the team immediately?
Well, what's fascinating here is that it's a deeply ingrained assumption in corporate culture that the person closest to the fire should lead the diagnosis. But the operational notes identify this as the misdirection of expertise.
Misdirection of expertise.
Yes. The person closest to a failure, the one currently feeling the heat and seeing the immediate symptoms, is frequently not the person best positioned to identify the structural root cause.
Because my perspective is too narrow in that exact second.
Your perspective is completely compromised by the immediate stress and the limited vantage point. The systems architect or the engineer sitting at a desk thousands of miles away, or even just in a different department, actually understands the underlying interdependencies.
Right.
In an emergency, your initial raw observations are often the only pristine data available. If you transmit your interpretation, your premature theory, you contaminate the data.
Oh, wow. You contaminate the data.
Yeah. The experts will waste critical minutes untangling your assumptions to figure out what is actually happening.
That means we need a strict discipline for how information flows when things go wrong. And the sources lay out a highly specific reporting sequence that anyone can adopt.
It's very simple, but very strict.
It goes like this: event, then observation, then instrument reading, and finally, diagnosis. The critical constraint here is that a diagnosis should only be offered when it is explicitly requested by the team.
Or when it can be defended with undeniable data.
Right.
You see the sequence executed flawlessly during the most famous crisis in space exploration, Apollo 13. When the oxygen tank exploded halfway to the moon, the crew did not jump on the radio to announce a catastrophe.
Even though it felt like one.
They didn't declare that a meteor had struck them, even though that was a very real possibility in their minds.
They started with the event. Houston, we've had a problem here.
Then they moved to the instrument reading. Jim Lovell reported a main B-bus undervolt.
Which meant they had a sudden drop in voltage on one of their power lines.
Exactly. Following that, Fred Hayes supplied the observation. He reported hearing a pretty large bang. They followed the discipline perfectly. Event, instrument, observation.
They didn't transmit a conclusion.
They did not. They waited until the conclusion was forced by the data, which happened about 14 minutes later, when Lovell looked out the window and saw a physical cloud of gas venting into the vacuum of space.
Because gas venting cannot be a sensor glitch.
Right, or a minor short circuit.
At that moment, the flight director back on Earth, Gene Kranz, locked down the communication loop with a directive that really should be mandatory training in every business. He told his team, "Let's solve the problem, but let's not make it any worse by guessing."
It is a profound directive because it validates the urgency of the situation while putting a hard boundary on the fear.
It forces the intellect to take over from the amygdala.
Exactly.
So we've covered how to navigate a sudden explosive disaster by swapping dramatic narration for precise sequences. But what happens when the stress isn't a loud bang, but a slow realization that you are completely lost?
That's a very different kind of stress.
How do you bound uncertainty when you are facing profound ambiguity and you truly do not know what is happening?
This requires a different kind of discipline, which is highlighted in the notes on Apollo 14. Alan Shepard and Ed Mitchell were walking on the lunar surface, attempting to navigate to a geological feature called Cone Crater.
And walking on the moon is incredibly disorienting.
Extremely. There's no atmosphere to scatter light or provide distance cues, and there are no familiar reference points like trees or roads to help the human brain calculate scale.
So a boulder that looks like it's 10 feet away could actually be the size of a house and a mile away.
Precisely. The terrain was steep, undulating, and totally deceptive. They were exhausted, their heart rates were spiking, and their oxygen supplies were getting tighter.
Not a good combination.
Yeah. No. They had a disagreement about their trajectory and thought they were nearing the rim of the massive crater, only to crest a ridge and find a smaller, unfamiliar depression. The temptation there, especially for a highly competitive pilot like Shepard, would be to make a confident guess to reassure mission control.
Of course.
But instead, Shepard got on the radio and stated, "Our positions are doubtful."
Our positions are doubtful.
Yeah.
It is such a concise admission of vulnerability, but strategically, it's brilliant.
It is a masterclass in bounding uncertainty. The lesson embedded here is that openly stating the actual size of your uncertainty is vastly more useful to a team than a confident but wrong estimate.
Or remaining silent out of pride.
Right. When you report a doubt rather than a guess, the organizational decision-making that follows is anchored in reality. Mission Control looked at their oxygen levels, accepted the uncertainty of their location, and ordered them to turn back.
And they later discovered from photographic analysis that they had likely been just 30 feet from the rim of Cone Crater. To travel all that way and miss it by 30 feet is heartbreaking. But the historical analysis points out something vital. Better judgment cannot compensate for missing inputs.
It's a huge takeaway.
Shepard and Mitchell didn't make a bad judgment call. The navigation failure was a fundamental failure of perceptual capability because the atmospheric inputs their brains relied on were gone.
Exactly.
If you or your team keep making defensible decisions that result in bad outcomes, you probably don't need to fix your judgment. You need better instruments. You need to fix the data you are feeding your judgment.
And managing that data brings us to the next layer of navigating ambiguity, routing attention deliberately.
Right.
Under extreme time pressure, a system or a person will always have more inputs than they can physically process. The most useful question to ask in that moment isn't, what should I pay attention to? The essential question is, what can only I handle and who or what will take the rest?
Here's where it gets really interesting. If you run a commercial kitchen, you know this dynamic intimately. Imagine you are the head chef during the Friday night dinner rush. You're holding a heavy pan of hot, popping oil.
Okay.
Suddenly, the grease trap on the stove catches fire. You cannot try to put out that fire yourself while simultaneously holding the boiling oil.
Obviously not.
That is how a contained problem becomes a catastrophic injury. You have to delegate the fire to the sous chef so you can safely manage the oil. You route your attention to the singular hazard that only you are in a position to handle. How did Neil Armstrong do this during the first lunar landing?
We see this exact attention routing during the Apollo 11 descent. 5 minutes into the powered descent, about 6,000 feet above the moon, a yellow caution light illuminates, and the computer throws a 12:02 program alarm.
Which indicates an overload, right?
Yes, the guidance computer is overloaded with data and is dropping tasks. Now, Neil Armstrong is flying a spacecraft toward a celestial body no human has ever landed on. He did not have the cognitive bandwidth or the time to diagnose a software overflow error.
He cannot fight the fire while holding the oil.
Exactly. So he routes the alarm entirely to Houston. He delegates the software problem to a 27-year-old flight controller named Steve Bales, who analyzes the telemetry and tells them they are go to continue despite the alarm.
Okay, so Houston has the alarm.
Meanwhile, Buzz Aldrin is next to Armstrong, continuously calling out the raw altitude and velocity numbers from the instruments. Armstrong has delegated the computer diagnosis to Houston, and he has delegated the instrument scanning to Aldrin.
Leaving his own attention entirely free to look out the window at the physical terrain.
Which was the one thing only he could do. And it was critical because the automatic targeting was flying them directly into a massive crater surrounded by boulders the size of cars.
Unbelievable.
Delegating the alarm was not avoiding the problem. It was the only way Armstrong could preserve enough attention to take manual control and fly the ship to a smooth area with just seconds of fuel remaining. It is strict attention control enforced under severe time pressure.
So we've covered reacting to the unexpected sudden emergencies and blinding ambiguity. Let's shift our focus to the risks we actively choose to take.
Okay.
The daily operational decisions where we know something might go wrong, but we decide to proceed anyway. How do we ensure we're actually managing those risks rather than just being reckless?
Well, the Apollo engineering culture demanded a very clear discipline for this. You must bound a risk before you accept it. We can look at the FMLAs on Apollo 15 and 16. On Apollo 15, they discovered a short circuit in the ignition circuitry of the main service propulsion engine.
Yes.
And on Apollo 16, the engine gimbals, which are the pivot mechanisms that steer the thrust of the engine nozzle, sort of like how a wrist steers a hand, they started oscillating wildly just before the lunar module was supposed to descend.
In a normal environment, those sound like immediate mission-ending failures.
They easily could have been. But the missions weren't blindly aborted, and more importantly, they didn't just cross their fingers and hope the hardware would hold together. In both cases, the risk was bounded.
How so?
The engineers on the ground ran aggressive tests. They reproduced the anomaly in simulators. They figured out exactly what the short circuit and the gimbal oscillation would and would not do. And then they attached the accepted risk to a specific procedural constraint.
Got it.
On Apollo 15, they developed and flew with brand new procedures to bypass the short circuit safely. On Apollo 16, they proved through simulation that the oscillations would damp out within a few seconds and wouldn't tear the engine apart.
So what does this all mean? It means that if you accept a risk at work, let's say you decide to launch a major software update, knowing there's an unresolved bug, or you sign a client knowing they have a history of moving goalposts, but you don't change anything about your behavior, your contracts, or your procedures, you aren't actually accepting risk.
No, you're not.
You're just being inattentive. You're closing your eyes. Accepting a risk requires a behavioral change to accommodate it.
That is a vital distinction, and it ties directly into how organizations handle safety margins and rehearsals. The engineers behind Apollo believed deeply in deliberate slack or unallocated margins.
Meaning extra capacity that isn't assigned to anything.
Exactly. But they had a strict rule. A reserve margin that has been assigned a specific task is no longer a reserve.
I love this. If your rainy day emergency fund is currently paying your monthly grocery bill, it is not an emergency fund anymore. It's just your checking account.
That's a perfect way to put it. On Apollo 11, the primary reason they survived that 1202 computer overload we discussed is because the software engineers had fought to keep a 10% margin of the computer's memory completely empty.
It had no pre-assigned function.
Right. So when the computer suddenly got hit with a flood of unexpected radar data, that unallocated 10% absorbed the computational blow just long enough to keep the spacecraft flying.
But that raises a question about their preparation. I mean, they rehearsed every single second of that mission in simulators. Why didn't they catch a massive radar data overload during the dry runs?
And if we connect this to the bigger picture, this gets to the hard truth about preparation. Rehearsals reduce the space of surprises, but they can never close it completely. The surprises will always emerge from whatever the rehearsal omitted.
Always.
On the Apollo 10 rehearsal flight, the crew never ran the landing radar and the rendezvous radar at the exact same time. It wasn't in the flight plan, so they didn't test it. But on Apollo 11, the crew left both radars on, and the hardware interaction caused the overload.
So what's the lesson?
The lesson from the notes is that before you trust any rehearsal, whether it is a dry run for a board presentation or load testing a backup server, you must deliberately name the ways it differs from the real event.
Because in the real event, the team might be fatigued, the network might be carrying live traffic, or the emotional stakes will alter people's behavior. The rehearsal is never the event.
And that reality leads to the final and perhaps most sobering lesson from these sources. The Apollo system was incredibly resilient when it came to surviving fast, highly visible failures. A lightning strike, a computer alarm, an exploding tank, the system caught those. But it was highly vulnerable to slow, upstream failures.
Right.
The tragedies and near misses of the program were almost always the result of a slow creep of small changes over years.
Let's talk about the mechanics of that, because it is so applicable to everyday business failures.
Yeah.
How did the Apollo 13 oxygen tank actually turn into a bomb?
Well, it wasn't a sudden manufacturing defect. Years before the flight, the internal thermostat in that oxygen tank was designed to handle 28 volts of electricity.
Yeah, okay.
But later on, the ground testing equipment at the facility was upgraded to 65 volts to speed up operations. The thermostat design inside the tank was never updated to match the new 65 volts standard.
Oh, man.
So during a routine ground test, that higher voltage literally welded the thermostat shut. It couldn't turn off. The internal heater stayed on and quietly baked the protective Teflon insulation off the wiring inside the tank.
And no one could see it.
No one saw it. When the crew flipped a routine fan switch in space weeks later, the exposed wires shorted, sparked, and blew the tank wide open.
It was a failure of configuration management across time. And the Apollo 1 fire on the launch pad was the same type of slow failure, right?
Yes, unfortunately. The Apollo 1 fire, which tragically killed 3 astronauts during a ground test, was the result of a slow accumulation of non-metallic materials like Velcro and nylon netting, creeping into the spacecraft cabin over years of design tweaks.
Just a little bit at a time.
Right. The engineers didn't fully account for how adding just a few square inches of convenience material at a time fundamentally altered the flammability of the cabin, especially in a pure oxygen environment. The dramatic fast recoveries get the historical headlines, but the slow distributed failures are the silent killers of any complex system.
The slow creep of small compromises.
Yeah.
It's rarely the sudden disaster that destroys a project. It's the tiny exceptions you made 2 years ago that suddenly interact in a deadly way today. Let's bring all this home. Today, we've unpacked a toolkit forged in the vacuum of space, ready for your next high-stress moment at work. Number 1, substitute precise measurement for dramatic narration. Do not panic out loud. Read the symptoms.
Right.
Number 2, enforce the strict reporting sequence of event, observation, instrument, and finally diagnosis. Number 3, when you are facing ambiguity, openly state the true size of your uncertainty so your team can make decisions based on reality.
Yep.
Number 4, route your attention to the singular hazard only you can handle and delegate the rest. And finally, never accept a risk without attaching a tangible behavioral change to it.
Because the legendary composure of those astronauts and controllers was not an accident of birth. It was manufactured through these exact operational rules.
It's all a system.
It's a system. It was a deliberate retention of enough cognitive attention under terrifying conditions to see the thing worth seeing and accurately describe what it was without letting fear contaminate the data.
So as we wrap up, I want to leave you with one final provocative thought to mull over. Think back to that metaphorical system failure at work we talked about at the very beginning. You now have the tools to handle the sudden fire.
The lightning strikes.
Right. But what about the slow smolder? What slow upstream changes are happening in your own career or your organization right now that your current safety checks and daily habits are completely blind to? The alarms might not be going off yet, but what is slowly changing while no one is looking? Keep your eyes open, measure reality precisely, and we'll see you on the next deep dive.